Thanks, Nikhil. Thanks for the introduction, and I'm happy to speak here. I know this is the last talk of the day, so I won't hold you hostage for long, and I'll try to keep it light. So this is joint work with Jaikumar Radhakrishnan at TIFR, and I should also thank Prahlad, who is in the audience, because he's helped me a lot with this work. And so I'm going to talk about the zero error list decoding capacity of the q by q minus 1 channel. And as you can see that the title has three main chunks to it: the zero error list decoding capacity and the q by q minus 1 channel, and I'll introduce them one by one. So let's get right into it. So what is the zero error capacity of a channel? Well, I guess many of you already know what it is, but nevertheless, this was introduced by Shannon in '56 in a seminal paper, and it tries to capture the rate at which you can transmit information across a channel with perfect recovery of information. So let me emphasize that what we really want to do is transmit information across a channel so that a decoder decodes with probability 1. And it's best understood via an example. So let's consider the famous typewriter channel. How does it behave? Well, the input alphabet are the English letters A, B, C through Z, and the output alphabet is the same. And when a particular symbol, say I, is input to the channel, it can output I, that is the same symbol, or the immediate successor J, right? And the green arrows in the diagram denote how the channel functions. Now, since we are supposed to decode with probability 1, unlike the Shannon model where you are supposed to decode with high probability, here there is no point in putting probabilities, the transition probability on the edges, because you can think of the noise as being adversarial. This kind of channel is best understood via the confusability graph, and unlike the name, the graph is actually very simple. What you are supposed to do is the vertex set is the input alphabet, so the English letters A, B, C through Z, and you put an edge between two input letters if they can be confused by the channel. So for instance, A and B can be confused by the channel because the output B is consistent with the input A and B according to this channel, right? So this is what the zero error capacity of a channel is. And this notion has received considerable attention in information theory, and it's a very difficult field to make progress in, because even many fundamental questions are still not well understood in this field. And I mean, yeah, just to point out, there was a seminal result of Lovash in '79 which determined the zero error capacity of C5, and it introduced the use of semi-definite programming. And if you change this 5 to 7, we are still hopeless. We don't have any idea of where the zero error capacity of C7 lies. So I just wanted to point out that this is not an easy notion to study, but nevertheless it has received considerable attention, and it's a very fundamental notion to ask for. And now let's go to the star of the show, the q by q minus 1 channel. So this was introduced by Peter Elias in '88. And as you can see, the channel, the input and output alphabet are the same as square bracket q, which is basically numbers 1, 2, 3 up to q. And how does the channel behave? When a particular symbol, say I, is input, you can output anything that is not I. So the green arrows here denote what can be output, and the red arrow denotes the fact that the channel cannot output I if the input is I. So we are going to study this channel under its zero error capacity. And for instance, we can take the 3 by 2 channel. So here there are 3 input symbols, 1, 2 and 3, and if the symbol 1 is input, then you can output 2 or 3 but not 1. That's how the channel behaves. And again, let me emphasize, what we want is to encode messages and send it across the channel in such a way so that the decoder decodes with probability 1. There is no probability of error. So let's take an alternate view of the channel now. So what are we going to do? We have a message space of cardinality m, and we are going to encode each message using a string of length n, where each coordinate of the string is going to be an input letter. So anything between 1, 2, 3 and q. So in this case, the rows of this matrix are supposed to represent the messages that we have, and each message is encoded using an n long string, and each string comes from 1, 2, 3 or 4, because I am taking q to be 4. So what you see over here is a subsection of this code book, which can be naturally viewed as an m cross n matrix. And what we are supposed to do is we are supposed to send one of the messages across the channel will corrupt it, and the decoder is supposed to decode with probability 1. But as many of you would have realized, unique decoding is just not possible in this channel, because for instance, we try to send the channel MX through the channel and try to send the message MX through the channel, and the q by q minus 1 channel corrupts it as I have shown over here. Then the decoder is hopeless, because there is no way for the decoder to know whether the message sent was MX or MY, because the q by q minus 1 channel can corrupt both the messages in a consistent way, and this you can just verify coordinate by coordinate. So here the output symbol 4 is consistent with the input symbol 1 and 2, and so on. So what do we do now? We sort of relax the demand on the decoder, and we use the notion of list decoding. So what we really want from the decoder is, since we cannot ask him to uniquely decode which message was given, we really want him to give us a list of L messages with the guarantee that the original message is in this list. And this notion is a very fundamental notion, and it's been used heavily in computer science and elsewhere. It was again introduced by Peter Elias in 57, and it helps to beat half the minimum distance barrier under the Hamming model. And but many of you would have also realized that actually, okay, fine, you can ask for a list of messages, but L cannot be too small. So what I want to say is that L at least needs to be q minus 1 in size, and that you can see again, because for instance, take this, suppose q is 4, and so what we are saying is that the decoder needs to produce lists of size at least 3, because the idea is that suppose the decoder could produce lists of size 2 and be sure about the original message. Just look at these 3 messages, MX, MY, MZ. Again the same problem occurs. The q by q minus 1 channel can corrupt all 3 of them in a consistent way, as you can again verify coordinate by coordinate, 1, 2, 3, and the coordinate 4 is a consistent corruption for these 3 input symbols, right. So the decoder has no way of knowing whether the message sent was MX, MY, or MZ. So he needs to produce a list of size at least 3. Now you might wonder, where is this going to stop? Well, it stops at 4 in this case, because the q by q minus 1 channel cannot confuse you with these 4 messages, MX, MY, MZ, and MW, because if you focus on the red column here, it has all the input symbols 1, 2, 3, and 4. So there is no consistent output that the q by q minus 1 channel can produce to confuse you. So at least on the face of it, it looks like q minus 1 should be enough. But let's take a different combinatorial view of our problem. So we are going to look at the code book as an M cross N matrix, as I have been saying. And what is our requirement? We require that for every set of L plus 1 rows, if we are list decoding with a list of size L, that is, we require that there is a column like the one in red over here, such that the entire input alphabet is seen in this column when I restrict my attention to just these rows. So for instance, here L is equal to 3 and Q is equal to 4 in this case. So what we really demand is every set of 4 rows, because L plus 1, there is a column, the red one, where we see the entire input alphabet 1, 2, 3, 4, right. So if you have not followed me till now, this is a correct time to sort of come back in, and you will not miss anything about what I said. So again, what we are interested in is, you should think of M as being large and going to infinity. What we are really interested in is the minimum value of N, because the smaller the value of N, the higher the rate we will get across this channel. So what have we got at this point? We have got a very elegant and combinatorial question, which is very simple to state. What we want is an M cross N matrix where each entry comes from 1, 2, 3 up to Q, such that for any L rows that I pick out, any L plus 1 rows that I pick out here, there is at least one column where I can see all the input alphabet, right. And this is exactly equivalent to the list decoding question that I had raised before.
So this is a sufficient condition, but why is it necessary as well?
Yeah, it's necessary because suppose you have some rows where there is no column where you see all the input alphabet, then the q by q minus 1 channel can corrupt these in a consistent way, and there will be no way for you to just know which.
In that position, that
yeah.
alphabet that you did not notice,
it can corrupt it, because what will happen is, suppose the symbol 1 is missed in this red column, then the q by q minus 1 channel is just going to output 1, because that's a consistent output. What you have seen in the red column is 2, 3 or 4, because you have not seen 1. So 1 is a consistent output for the q by q minus 1 channel to give here. Yeah, and you can pretty much see it's equivalent, because if you don't miss it, then there is no way for the q by q minus 1 channel to confuse you. If you do miss it, then the q by q minus 1 channel can confuse you, coordinate by coordinate. So all you need is a single coordinate where you see everything, you see all the input alphabet. Yeah, so this is just an equivalent question, and
What was Elias's motivation
to study the q by q minus 1 channel. So he started off with defining the 3 by 2 channel, and then he said that okay, you can also consider the q by q minus 1 channel, and I think he just wanted to study it because it looked like a very nice, I mean it looked like a natural channel to him for the combinatorics that arose out of it. I am not really sure what exactly motivated him.
Was he also interested in list decoding?
Yeah, because 3 by 2 there is no, you cannot uniquely decode, so you have to list decode.
He was interested in it in the decoding.
Yeah, in the decoding part, sorry, yeah. So anyways, before I move on, I just want to say that the formulation is equivalent to the combinatorial problem we had described, right. So just to sort of have some formal footing in the talk, what are the quantities of interest we have? Well, I have already told you what a zero error code is. It is just this m cross n matrix with the property I was suggesting. And what is the zero error capacity with list size L? It is just the maximum rate R you can achieve, such that there is a zero error code of size 2 to the nr. Or alternatively, you can think of as trying to minimize n for a given value of m, right. So we want n to be as small as possible so that we get such an m cross n matrix. Now let me state the result. So before that, let me give some context so that I can put the result in perspective. So for q equal to 3, this problem has received considerable attention, and this was called the preference problem, and it was mentioned by Kerner in the Shannon lecture at ISIT 14. As you can see, for different values of q and L, where L is the list size, this problem has been attacked by various authors, and even as recently as 2017, where Dalai Guruswamy and Radhakrishnan put better bounds on the 4 by 3 capacity. So, but we are not going to be interested in that regime of parameters. What we are going to be interested in is for results for large values of q and L. So you should think of the alphabet size as being large. What bounds can you put then? So, so first such result comes from a beautiful paper of Fredman and Komlosh all the way back in 1984, where if you look at the q by q minus 1, that is, you have an input alphabet of size q and you are list decoding with lists of size q minus 1. What they show is that n, that is the number of columns or the block length of in the matrix that we were talking about, it has to grow exponential in q times logarithmic in m, right. And you can see that I put a lower bound over here, but in the previous table there was an upper bound here. This is simply because there I was talking about the capacity, here I am talking about n, and they are inversely related. It is the same thing. And what is achievable, where our only tool is a random code, and the random code says that basically what they prove is tight, that you can construct an m cross n matrix with the property where n grows exponential in q times logarithmic in m. So the next result in this line comes from Kerner in 86, where he showed that actually if you allow the list size to grow by just one more, that is your demand was a list of size q minus 1 from the decoder, now you ask for a list of size q. So it's an easier problem. So proving a lower bound was tougher, but he managed to prove an exponential in q times a logarithmic in m lower bound. He said that pretty much this dependence does not go away even if you let the list size grow by 1. And of course, if you could list decode with size q minus 1, you can list decode with size q, right. And then there is a long pause, and all the way in 2006, where Chakrabarti, Radhakrishnan, Raghunathan and Sasade proved that actually you can let the list size grow to even 1.58 q, that is a constant factor away from q. And even then pretty much the same dependence, same lower bound keeps on holding, that you need to take an exponential hit in q times a logarithmic hit in m, right. And you might ask, where am I going with this? But not too far, because at q ln q, the random code will already start saying that, oh, you know, the exponential dependence in q goes away. That is, when you are asking for such large list sizes, which is an easier problem, the upper bound actually improves from exponential in q times logarithmic in m to q times logarithmic in m. And you can show that that is also pretty much tight using a simple argument. And why I have written the coupon collector is the process that gives you this upper bound is very akin to the coupon collector process, and I will allude to it later. But as you can see, there is this annoying gap in between 1.58q and q ln q, where we don't really understand where this behavior suddenly changes from a polynomial in q times logarithmic in m to an exponential in q times logarithmic in m, right? And this is exactly where our result comes in. What we show in this work is that actually even if you go to a constant factor of q ln q, that is q ln q by 5 here, what happens is that morally your exponential dependence in q doesn't vanish away, right? That is the work we show, and of course there is this upper bound which still continues to hold because it was here at q minus 1. Let me put it in a picture, because a picture speaks 1024 words, so it's best to put things in a pictorial way. So what we had here is a capacity versus alphabet size curve, and as you can see that at L equal to Q, if you combine Friedman, Komlosch and Corner as I was talking about, what you really realize is that the curve is going to go exponential in Q, and this is CRRS, who said that even at L equal to 1.58 Q, this curve, this capacity versus alphabet curve is going to decay exponentially in Q. And we already know by a random code construction that at Q ln Q, the curve actually decays only inverse polynomially, right? And then so it's a natural question to ask, when does this capacity curve become inverse polynomial? And this is exactly where our result fits in. We show that even if you push the list size all the way up to q ln q by 5, morally your curve still decays inverse exponentially, right? And just as a remark, these were the two conjectures raised in their paper, and the result resolves both of them. Moving on, okay, so this slide is just not for you to see, it is just so that you can catch my lies that I have been sort of hiding this polynomial change and this lambda and all, but yeah, just to put something there. Now let's move on to a proof idea, right? So I hope this is a second chance for you to sort of zoom back in if you have lost me. So what we really need is an m cross n matrix such that for all set of L plus 1 rows, there is a column H where you see the entire input alphabet. This is our problem. We are going to think of Q as being large and M as going to infinity, right? And the building block of all the works that I presented, except for Corners, was the Friedman-Komlosch framework they had in their paper in '84. So I've been told that when you present your work, it's the preliminaries that people pick up well and not actually what you present. So I hope that you guys at least pick up the Friedman-Komlosch framework well, and it's a very beautiful framework. So let's just see what it is. So let's first look at two easy bounds on n. So we are trying to minimize n on n when L is equal to q minus 1. So for every set of q rows, you want h of r to equal, there should be at least one column where h of r is equal to the entire input alphabet, right? So the first bound just comes from asking yourself, okay, if I look at a particular column H, right, how many r's of size q are there such that hr will equal q when I restrict my attention just to this column? Well, that is a simple answer, because you will realize that it's best to sort of distribute in this column, it's best to distribute the symbols equitably, in which case, yeah, these are just some simple calculations, so don't pay too much attention to this, but to the idea. In this case, you will see that each column can take care of about m by q to the q sets of rows, and the total set of rows that you have to take care of are m choose q. So that puts an immediate lower bound on n, which looks like exponential in q. The second lower bound they get is by this pruning idea, where they say that, let's look at our code book, let's look at the first column, and let's look at the most unpopular symbol in that column. Let's say it's 3, and then they just delete these rows. So you are reducing, you are taking a hit of q minus 1 by q in your universe size of m every time you do this. So this is what I will call pruning. Then they go on to the next column, they delete more rows. At the end, when they have gone through all columns, they must be left with less than q rows, because the point is you have ensured that whatever is left after this pruning process has missed at least one symbol in any column. So then you could not have met your demand if the number of rows you are left with is greater than q, right? And that, if you just put the numbers together, it turns out that this gives you n is greater than log m, right? But this doesn't quite give us our bound, because our bound was a multiplication of the two bounds, right? And that is where the cleverness comes in. What they do is that, we have seen these two simple bounds, Now we are going to apply those two bounds in a slightly randomized fashion. So what they do is that they say let's pick up a set of q minus 2 rows randomly from our code book, right. What would you expect if you do that? Well, you would expect that in most of the columns you will see much fewer than q minus 2 symbols. If you are picking rows at random, it's highly unlikely that that you will see in a particular column all the q minus 2 symbols that you have picked up to be different, right. There is a good probability that you will actually pick up the same symbol you picked up before. So you will see collisions, and there will be, and this is a very simple calculation, not very difficult, which just shows that actually there will be only an exponentially small fraction of columns where the number of symbols you collect will be q minus 2, right. And then they say, oh, that's great, we will just run the last pruning argument on the red fraction of the matrix, that is on the bad columns. So if you prune against the bad columns, what happens is the n gets proxied by an exponentially small quantity in q times n, because you are actually only pruning against such few number of columns now instead of pruning against everything. So that gives you the bound you need. You get n is larger than exponential in q times logarithmic in m. So that was their idea. This was pretty nice and neat idea, but unfortunately this idea doesn't get you anywhere beyond list size q minus 1, which is what they studied it at, and they were not studying it for the q by q minus 1 channel, they were studying it for perfect hash families, but their result implies a bound for the q by q minus 1 channel as well. But let's move on. So before we move on to higher list sizes, I thought it will be instructive if we just look at the upper bound at q ln q that the random code gives. So what are we going to do? We are going to fill our code book randomly, and we want to minimize the number of columns we use. But if we are filling symbols at random, and let's look at a particular column h that is in red over here, and when the list size you are interested in is of the order q ln q, there is actually a very good probability that a random filling of the symbols here will give you all this, will make sure that HR is what R sees over here is q, that is the entire input alphabet, right. And this is just very similar to the coupon collector problem, where you are supposed to throw uniformly at random probes into a universe of size q, and you are supposed to pick out all the symbols. And we know this problem very well. We know that at around q ln q probes we see the entire input alphabet, or we pick up all the coupons in their terminology. And and then what do? You just run a union bound over all the possible rows of size q ln q, because you need to ensure that any set of q ln q rows has a column where it sees all the symbols, and that simple calculation just gives that n should be like q log m, right. But the reason I presented this is because I would like to emphasize that the coupon collector also tells us that this random code book that we constructed will fail miserably at q ln q minus cq, because the coupon collector process has a very sharp threshold. That is it's almost a deterministic statement that at q ln q minus cq you will not pick up all the coupons. So anyways, I just want you to keep this in the back of your mind. So let's move on to what CRRS did for getting a bound of 1.58q. Well, they basically beat Friedman-Komlotz at their own game. They say that, okay, what we are going to do is we are going to do pretty much what Friedman-Komlotz did, but we are going to make one small observation. We are going to say that most of the columns actually see much smaller than q times 1 minus 1 over e symbols, rather than just saying that they see much fewer than q minus 2 symbols, right. And this is again a simple expectation calculation and using some concentration inequalities. And they realize that an exponentially, again they are in the same Friedman-Komlotz situation, an exponentially small fraction of the columns are bad, where you see much larger than q times 1 minus 1 over e symbols, or in fact strictly larger. And then they just say that, okay, now what do? Let's prune against these bad columns. So they restrict their attention to just these rows of the universe, because they have pruned against the columns, so they have deleted some rows. And then they say that, okay, at this stage we can afford to pick more rows, because we have only collected in the good columns, I have only collected q times 1 minus 1 over e symbols, and the bad columns I have already made ineffective by restricting my attention to only the yellow rows, right. And they say that, okay, let's just repeat the process iteratively now. Let's just pick up q by e minus 2 rows and try to continue with the process like Friedman-Komlotz did. And this iterative, so let me just show it again. So you pick a set of rows which is q minus 2 in cardinality, and you get a few bad columns, and then you prune, then you again pick up some rows, then you again get bad columns, then you again prune, then you again pick up an appropriate number of rows, and you continue this process as long as you can. And in the end, the rows that we pick up, however many rows we can pick up without collecting all the symbols, is our bound on the list size, right? And the thing is that this process stops, as you can see, it's building up a geometric series, 1 by e, 1 by e square, and so on. So that geometric series is exactly 1.58q, and this process stops there. So this is why they are stuck at this bound. And but a closer analysis will show you why their bound is weak. I mean, we saw that in the coupon collector process that I was mentioning. At q ln q minus cq itself, it was failing miserably. I mean, the n you would calculate there for a random construction will turn out to be exponential in q times log m instead of polynomial in q times log m. So you could wonder what is it that their process is not able to capture? Why is it not able to imitate the upper bound and reverse it? The reason for that is the way they analyze how many symbols they have collected is very weak. So let's look at it stage by stage. So in the first stage, they collect q minus 2 rows, and the image size in the good columns, that is the columns which are not red, is like q times 1 minus 1 over e. That was the definition of a good column, and they showed that an exponentially small fraction will be bad. They prune against it. They pick up a list size of q by e minus 2 in the next iteration, and then they say that the image size is q times 1 minus 1 over e square, and so on, so on. They keep on analyzing this. But the reason why it's not good is because the way they analyze this quantity. So what they are supposed to analyze is the number of symbols collected here union the number of symbols collected here. The way they analyze this is just by adding the number of symbols they have collected here and adding the number of symbols they have collected here, which is an obvious upper bound, but it's not good because it doesn't capture the collisions that you are supposed to see across the iterations. And that is what actually happens in a coupon collector process, right? As once you have collected a lot of coupons, collecting the next coupon is very troublesome because most likely you will be collecting the coupons you have already collected. So this is exactly why the process is unable to imitate the coupon collector. And yeah, so this is what I have been talking about, that they need to account for symbols which are common between these two parts, and they need to capture these interlevel collisions which they were not able to. So let me just state it again. What do? They just iteratively repeat Friedman-Komlosch, and the limitation is that they are unable to mimic the coupon collector because they are not able to capture collisions. They simply use a very trivial bound, which is HR1 plus HR2. And what is our idea? Well, our idea is to sort of repeat Friedman-Komlosch and CRRS, but in a more pseudo-random way. What we do is, instead of choosing one set of cardinality q minus 2, we choose many sets of cardinality q minus 2, such that the number, and we declare a column bad if again we see too many symbols, more than what we expect. And we have to be careful with how many rows we choose here. We choose an ensemble, so we have to be careful about the size of the ensemble because we need to keep the number of bad columns to be still an exponentially small fraction. And then we prune against these bad columns. We pick up a new row of size q minus e by 2 like Friedman-Komlosch were. But now to estimate how many symbols we have collected, we can do the following trick. Now from the ensemble that we chose earlier, we can choose a random set from our ensemble and ask how many collisions have happened between this random set and HR2 that we have collected, right? And somehow this way of doing it in a pseudo-random fashion where helps us capture the collision between these two symbol sets that I was talking about. And the idea basically then is to keep on iterating this like CRRS were. And so in the next stage also we pick an ensemble and we compose these two because we need to go to another iteration and so on. And this is it's not very straightforward to do this, but there are some technical nuances that arise. But basically the idea was just to replace their entire argument on a pseudo-random space of ensembles. And this is just to sort of summarize. We replaced the entire space on which the argument was happening with a pseudo-random space. And yeah, this poses some technical difficulties, but we are able to get around them. And I'm sorry if I'm not making a lot of sense, but this is sort of to bait you to read the paper rather than just say what is in there. And in the end, I would like to say that what we did is we were able to imitate the coupon collector more faithfully. And we could prove that the list decoding capacity up to q ln q by 5 decays exponentially morally. And but this still leaves an open question. If what we are all the proofs that I showed you are, if they are trying to imitate the coupon collector and reverse it, then we should really be expecting exponential decay all the way up to q ln q minus cq, where the coupon collector says there is a sharp threshold. And that is what we are not been able to do, and it's been a question which has enchanted me for a long time, but it's somehow very difficult to get to that threshold level. What we can get to right now is q ln q by 5. So thank you for your time.
Any questions for Siddharth?